A slender rod. A slender rod with length capital L has a mass per unit length that varies with distance from the left end, where x is equal to 0, according to dm dx is equal to gamma times x, where gamma has units of kilograms per meter square. Part A, calculate the total mass of the rod in terms of gamma and L. So let's start with part A. We have a linear mass density lambda, which is space varying gamma times x, that's equal to dm dx. So how can we calculate the total mass of this rod? The total mass will be the integral from x equals 0 to L dm. So if we calculate the mass of a mass element and integrate over all such mass elements from 0 to L, we will be basically calculating the total mass. So this will be integral from 0 to L gamma times x dx. This will be gamma times x squared over 2 when integrated, which is to be evaluated between x equals 0 and x equals capital L. So gamma times capital L squared divided by 2 will be equal to the total mass capital M. So we find that gamma is equal to 2 capital M divided by L squared, and it has units of kilograms per meter square. Okay, so indeed we find using this mass per unit length that varies with distance from the left end, gamma times x. The total mass of the rod is integral 0 to L dm, so we integrate over all mass elements and we obtain integral gamma x dx, which gives us gamma L squared over 2 as our final answer. So let's move on to part B. Calculate the moment of inertia of the rod for an axis at the left end, perpendicular to the rod. Use the expression you derived in part A to express I in terms of capital M and capital L. How does your result compare to that of a uniform rod? Explain. Now, at the left end, we have this z-axis, which is our rotation axis, perpendicular to the plane. So the moment of inertia with respect to the z-axis will be integral r square dm. Now, if I have a mass element on this rod, you can see at a distance x from this rotation axis, it will have a distance x, so r square will be x square, and then it will have a mass dm, which I have to calculate. So this will be equal to integral x square lambda dx, where x will go from 0 to capital L. So this will give me integral from 0 to capital L x square gamma x dx. Gamma x is my lambda, so this will be gamma x to the 4th power divided by 4, which will be evaluated between x equals 0 and x equals L. So I find that the moment of inertia with respect to z-axis is gamma L to the 4 divided by 4. But since I know what gamma is from part A, for gamma I substitute 2 capital M over L square multiplied by L to the 4 divided by 4. We obtain L square makes this L to the 4th L square, and this 2 will make this 4 2 capital M capital L squared divided by 2. Now I want to compare this to a uniform rod. Now if this were a uniform rod for a uniform mass distribution, I would have lambda, the linear mass density, equal to the total mass capital M divided by the total length L. In which case, my moment of inertia with respect to the z-axis would be equal to integral lambda x squared dx lambda x cubed over 3, because lambda does not depend on x, where lambda, this will be evaluated between 0 and capital L, where lambda is a constant, capital M over L, multiplied with L cubed divided by 3, I would obtain mL squared divided by 3. So this is the uniform rod case. Uniform rod and non-uniform rod compare. So we have uniform rod, lambda is equal to capital M over L, does not depend on x, in which case Iz is equal to mL squared divided by 3. For the non-uniform rod, with linear dependence on x, lambda is equal to gamma times x. The moment of inertia with respect to the z-axis is capital ML squared divided by 2. So I see that the moment of inertia, Iz, is higher for the non-uniform rod. And since the mass increases linearly with x, the contribution from the farther mass elements increase, because I have an increasing mass, and as r increases, mass also increases, so r squared dm increases, so we have a larger contribution from the farther mass elements. Part C. Now repeat part B for an axis at the right end of the rod. How do the results for parts B and C compare? Explain. Now part C, I put my rotation axis at the right side. So now if I take a mass element dm at position x, it's at a distance capital L minus x from the right hand side. So the moment of inertia with respect to the right side will be integral from 0 to L r squared dm. Now r is L minus x, so it's L minus x squared dm. So this will be integral from 0 to capital L, L minus x squared lambda dx, which is my dm. And this is the integral from 0 to L, capital L minus x squared gamma times x dx. So my moment of inertia with respect to the right side will become integral from 0 to capital L. So if I open up L minus x parentheses squared, L squared minus 2Lx plus x squared multiplied with gamma x dx. This will be the integral from 0 to L, L squared x, the first term, minus 2lx squared, the second term, x cubed, the third term, gamma dx. So if I perform the integration, I obtain L squared x squared divided by 2 for the first term minus 2L x cubed divided by 3 for the second term and x to the fourth power divided by 4 for the third term. This will be evaluated between 0 and L and multiplied with gamma. So this will give us L squared multiplied with L squared over 2, L to the fourth power divided by 2, minus 2L L cubed over 3, so 2L to the fourth power divided by 3, and finally we have x to the 4 over 4 becomes L to the 4 over 4. Evaluated at 0, all the terms will give 0. So this has to be multiplied with gamma. Now I recall that my gamma was 2 capital M divided by L squared. So this will be, let's make everything common denominator. So to make this 12, I have to multiply it by 3. 3L to the 4 over 12. So that will be 3L to the 4. Or let's start with the first term here. So this has to be multiplied by 6. 6L to the 4 over 12. So I will have 6L to the 4. And multiply this by 4. 12. 8L to the 4 over 12. So minus 8L to the 4. And plus 3L to the 4 divided by 12, common denominator, parentheses. So this gives us 2 capital M divided by L squared multiplied with 6 plus 3, 9, minus 8, 1, L to the 4 divided by 12, which is capital M, capital L squared divided by 6. So 2 will make this 12, 6. So this is our final answer. Now, I find that the moment of inertia for the right-hand side, rotation axis on the right-hand side, will be ml squared over 6, which will be less than the moment of inertia for the left-hand side, which is ml squared over 2. Now, since the mass on the right side is larger, in the moment of inertia integral, the larger mass contribution is multiplied by smaller r square values, so the overall moment of inertia will decrease. In fact, when r is equal to 0 at the right end, which has the largest mass, we will have no contribution to the moment of inertia. Therefore, this result is expected. The moment of inertia should be less when the axis, the rotation axis, is on the right-hand side. So this basically completes the solution to this problem, but I want to elaborate on this a little bit more. So one thing I want you to notice is that if I try to use the parallel axis theorem of some sort, the moment of inertia on the right hand side is not equal to the moment of inertia on the left hand side plus capital ML squared, where L is the distance between the two. This would be equal to ML squared over 2 plus ML squared, which is 3ML squared over 2. So that's not equal to that. And why is that equal? Because the parallel axis theorem, let's recall the parallel axis theorem, is stating that the moment of inertia on the right hand side is the center of mass moment of inertia plus md squared. So this will be equal to I center of mass plus ml squared we have to find the location of the center of mass to basically calculate it using this theorem. So let's do that. Let's find the for exercise the center of mass of this rod. So x center of mass, the location of the center of mass, is integral x dm divided by the total mass capital M. So if I'm at a distance x here, I have a mass dm. So each one will have a contribution x dm. So the center of mass is integral x dm divided by m. So this will be integral from 0 to capital L x lambda dx divided by capital M. And this is integral from 0 to L x gamma x dx divided by capital M. So this is gamma divided by capital M x cubed over 3 evaluated between 0 and L. Gamma is 2 capital M divided by L squared multiplied with 1 over M multiplied with L cubed over 3. This gives us M's cancel. L squared cancels L cubed, makes it L. 2L divided by 3. So the center of mass is located, as you can see here, at 2L divided by 3. So what is the moment of inertia with respect to the center of mass? It's integral r squared dm, integral from 0 to L. So if I'm at a distance x with respect to the left-hand side, I'm at a distance 2L over 3 minus x with respect to the center of mass. So it will be 2L over 3 minus x squared gamma x dx, where x goes from 0 to L. So this will give me integral from 0 to capital L. So if I open up this square of the parentheses, 4L squared divided by 9 minus 4LX divided by 3 plus x squared multiplied with gamma x dx. So this integral will become 0 to L 4L squared x divided by 9 minus 4L x squared divided by 3 plus x cubed gamma dx. So if I perform this integral, I will have from x square over 2, so that will give me 2L square x square divided by 9. The second term, x squared, will become x cubed over 3, so it will be 4L x cubed, 3 times 3, I obtain 9. And the last term is integral of x cubed is x to the 4 over 4, multiplied with gamma, evaluated between 0 and capital L. So this will give me 2L to the 4 divided by 9 minus 4L to the 4 divided by 9 plus L to the 4 divided by 4 multiplied with gamma, which is 2m divided by L squared. So common denominator is 36. So to obtain 36, I multiply this by 4. So I have 8L to the 4 minus 16L to the 4 plus 9L to the 4 divided by 36 multiplied with 2m over L squared. So this gives me an answer because 2 will make this 18, and I have 8 plus 9, 17 minus 16, 1. So this will become mL squared over 18. So that's the moment of inertia with respect to the center of mass. Now you can see that the distance between the center of mass and the right hand side is now 2L over 3 and L, it's L over 3. So I can calculate the center of mass using the parallel axis theorem. Then parallel axis theorem basically states that the moment of inertia for the right end will be I center of mass plus md squared, where d is L over 3, so it's mL squared over 18 plus mL squared over 9, because the distance between them here is L over 3. This will give me mL squared plus 2mL squared over 18, which is mL squared over 6. The same result I have found in part C of the problem, so by doing the calculation directly. So you can see that the proper use of the parallel axis theorem is I center of mass plus md squared. So you cannot calculate IR as IZ plus mL squared, so that would be a big mistake. All right, so we have considered the case of a non-uniform mass distribution in a rod where the mass increases linearly from left to right. In order to calculate the total mass, we integrate from 0 to L dm all the mass elements, and that gives us the value of gamma. In order to calculate the moment of inertia for the left end, we find the distance between mass elements at position x with respect to the left hand, which is x, so integral x squared lambda dx, where for gamma we substitute 2mL squared in gamma times x of lambda, so that gives us mL squared over 2. For the uniform case where lambda comes out of the integral as capital M over L, it's mL squared over 3. So we see that the non-uniform rod has a higher moment of inertia because it has larger masses at larger distances, so larger contributions from the farthest masses. And if we put the rotation axis at the right end, now when we are at position x, we are at a distance L minus x with respect to this rotation axis. So we perform the integral again, being careful with the distance between the rotation axis and the mass element being L minus x. So we obtain ml squared over 6. And we find that when we put it at the right side, it is less than Iz ml squared over 2 because the largest masses will have smaller distances r. So in fact r is equal to 0 will correspond to the maximum mass with 0 contribution because r squared dm will be 0. And finally I note that I cannot calculate the moment of inertia for the right end by taking the left end and adding to it ml squared, where L is the distance between the two parallel rotation axes. The proper use of the parallel axis theorem is I center of mass plus md squared. I can locate the center of mass integral x dm over total mass, which gives me 2L over 3 for the center of mass location. I notice that the distance between the two rotation axes is L over 3, so ml squared over 18 is what I find for the center of mass moment of inertia by noting that the distance between mass elements and center of mass is 12 over 3 minus x, as x goes from 0 to L, and I center of mass plus md squared, where d is L over 3, indeed gives me the same answer I have found in part C.